Hi everyone. So, so this is basically an extra class as mandated by NPTEL. So usually, I think what I would have ideally like to done today is teach you something called P4. Right? I could have done this, but since you have assignments every week, so I thought I'll finish off the actual uh, questions to be discussed by that you can easily answer your assignments. And this data plane programming, right? Whatever I wanted to take up, it will be done this Tuesday, right? Yeah, this Tuesday. So again, what to before going into this, what to expect is data. I mean, the next class, that is data plane programming. It's a practical, hands-on approach. Because I felt since you have studied advanced computer networking, right? And over the weeks, we've seen how when the protocols involved in traditional networking, and then we've seen some hypothetical concepts as well, like NDN, named networking, is one such hypothetical concept. But in between all of this, if you remember, right, I don't know how many of you remember this, you would have come across something called data plane programming. So you would have come across something called data plane programming. And this data plane programming would have introduced something called P4, if you remember. So this P4 is nothing but a language to program network devices. Right. So this was what was brought up, and you would have gone through some basics. There's a whole video on P4 as to how it handles it based on stages. Right. So this is the theoretical approach to P4. You would have seen it, but how does this P4 programming actually work? We can have a visualization as well as a practical demonstration using VMs, right? So that you can connect whatever you've learned in this journey to practical applications or to something tangible, something that you can even work on. Because this is all in the domain of current research. Right? So this shall be done on next Tuesday, right? But today it is named data networking. Now, again, I don't know if you've seen the videos, but I'm assuming you've seen the videos. So it's okay if you have not seen the videos also. Since this session will be recorded, you can always go back, watch the videos, and come back and watch these videos as well, right? So let's just, as usual, jump into some questions and try to understand NDN through these questions. All right, and just like last time, probably start writing some of these things down. That'll be more helpful for you. Instead of just me talking, I can just write some of these concepts down as well, right? When the appropriate or the correct question comes up. Right. So let's get started. Okay. So again, so Indian architecture is something that we looked at last time also. It was just mentioned in a fleeting way, but this time it's been looked at with a bigger lens, right? So the first question they're asking is how many packets are used in Indian architecture to retrieve a named chunk from a content provider? Right. So you can answer these questions on the chat if you want, or you can just be a passive listener and just observe. It's completely fine. Right, so this Indian architecture, right? It comes from um, the previous classes that we saw where we study ICN, and it's a specific architecture, and it is basically um, a paradigm where resources on the internet are identified by the name itself. Right. So just a bit of background. Indian is a proposed future internet architecture that shift the focus from where, right? Which is basically, let's say, just the IP address to what. Instead of sending packets to specific locations, communication is driven by the names of data, right? Also, some more context. So if you look at how Indian works, I'm just summarizing the whole videos, I guess, in one or two sentences. So you can just bear with me. The first thing is interest packets, a consumer sensor, interest packet, which basically requests a piece of content by its name, right? And then now comes the data packet. Once a content provider or an intermediate cache, right, receives the interest packet, that is, it responds with a data packet that carries the requested content along with its name and the producer signature. Right. So basically, these signatures, they establish the fact that it has originated from where it actually claims to have originated from. And so basically, it's an interplay between interest packets and data packets. It's pretty intuitive here. So you send a data packet and then, you send an interest packet and then you get a data packet. And the data packet is also going to contain the particular data that you asked for, also with proper verified signatures, which prove that it is from where it says it's from. So that you can basically be sure that whatever you received is exactly what you asked for, and not a man in the middle has come and kind of hijacked the whole thing. Right. This is basically how Indian works. Um, so coming back to the question, right? So how many packets are used in Indian architecture to receive a named chunk from a content provider? So how many packets are there here? There is one interest packet and one data packet, right? So the answer is, of course, two. So this is wrong, wrong, wrong. Of course, 1 and 3 and 4. We don't have to reason it out even. Yeah. I think I should give more space between these from now on. So how does Endian handle data caching? So what is data caching? So basically, it's when, let's say, you're the computer. So you are requesting something from the server, right? request, let's say, data A. So this data A, while it is on the way like this, right? There are chances where there are some middle boxes which can cache the data A. Right? So the next time you request, you'll get the answer right from A. So there's A. And a simple example for this is DNS architecture. If you've studied about it, DNS caching, where you cache the IP addresses of the domain names in the closest node to you. So basically, this data A is cached here. So similarly, in the NDN architecture, right? So what happens? How does NDN handle um, data caching, right? How important is it to? So I'll just write down a little bit about it. So that this will serve as some sort of a summarization for what NDN is also. You can just refer this and you can probably understand. One of NDN's core features is its in-network caching ability. Unlike traditional IP network, traditional IP networks are, this is basically what I said here. The current paradigm, whatever we're using in the world right now, is IP networks. NDN routers, right? NDN routers can store copies of data packets themselves as they pass through. Although, see, these data packets, they could vary in size. There is also this fundamental issue of what to cache, how much can you cache, right? And so these NDN routers are also intermediate routers, right? Again, all those practical um, constraints aside, this is how NDN was proposed to work. And very similar to that, when you get a response, right? A data packet is a response. It can cache that data packet somewhere close by here. And the whole packet is basically cached. The next time the same interest packet asking for the same resource comes up, you serve it from this particular location itself. And so this is essentially how it is supposed to work. So when a data packet traverses the network, right, intermediate routers can cache the data, and this cache data can be used to satisfy future interests for the same content. So what is the advantage? It reduces redundancy and latency. It reduces both of these. Right. Also, caching on intermediate nodes. is fundamental to NDN. It improves network efficiency, it reduces duplicate transmissions, and it speeds up data retrievals. Okay, it speeds up data retrieval. It's all a consequence of how NDN works. Okay, so now let's go back to the question. So how does NDN handle data caching? Again, very straightforward answer because by caching data on end user devices, no, that means you're talking about this, which is not the case. There's no caching data on intermediate nodes, yes, and these are nothing but intermediate routers. But caching data on a centralized server, nope. This is a centralized server, and this is also not where the data is cached, because that's the origination of the data, right? NDN does not support data caching, no, absolutely not. So the answer is B. These are pretty simple questions, but yeah. Just one moment. Right. So which are the following statements is/are correct about NDN? So this is a multiple choice, right? So which of the following statements are? It could be one, it could be two, it could be three or four, anything. So let's look at the first one. So NDN network, like IP packet delivery, employs best effort data retrieval, right? So this is best effort. So this is correct. So let's look at why this is correct. Okay. So what happens in traditional IP networks? Right. In traditional IP networks, data is delivered on a best effort, best effort basis, without guarantees of successful delivery. There is no guarantee for a successful delivery here, but it sends it. So what does this mean? It's like, so if you request something from a server, um, the server sends back your data, hoping that it'll reach you. And what is the paradigm of this hoping that it'll reach you in terms of protocols there? So if in case it does not reach you in traditional IP networks, what is employed? It is something called retransmissions, right? I mean, I don't want to go back into the basics of TCP/IP, but retransmissions ensure that if any packet is lost, that particular packet is retransmitted. And how is this done? This is using sequence numbers, etc., etc. Right? So this is basically how traditional IP networks work. So NDN changes the content retrieval paradigm, right? And still does not offer a guaranteed delivery mechanism. Which means basically in both these paradigms, basically in both these paradigms, network conditions may lead to data loss or a delay. Okay. And so NDN basically it introduces new mechanisms, right? And what are these? These could be what we discussed just before, which is content caching, or network data retrieval. But even though it introduces these mechanisms, it fundamentally still uses um, a best effort approach. In case a packet is lost, it is retransmitted using mechanisms which could probably piggyback on the concepts used by IP networks. Right? Okay. So now we know that A is correct. Like let's look at B. So B says NDN has a stateless data plane, whereas IP has a stateful data plane. Okay. So I'll give you the explanation for B. Right? So they're saying NDN has a stateless data plane, right? So again, the answer for this question is A. That's all. But what about B? The NDN routers. I mean, I'm writing this down because we can learn more about NDN this way. That's pretty much right. As I go, I think the amount of writing will come down. So just bear with me. Keep state. In the form of pending interest payable, right, or outstanding request. So this makes the data plane stateful. So in contrast, IP data plane is considered stateless with respect to per packet forwarding. So which is why this statement is wrong in more of a sense that it should be switched out. So NDN could have a stateful data plane, but IP does not have a stateful data plane. Right? So if they switch this, and if I give you, you should probably go with that answer as well as true, which could be possible in your final, right? And yeah. And what do they say next? They say IP includes a security primitive directly at the network layer, right? So this is a very good question actually because we can. Okay. Hmm. Should I read this beforehand? So what does C say? C basically says that IP includes a security primitive directly at the network layer. So basically, IP does not natively include primitive at the network layer security is typically handled at higher layers, right? Using additional protocols like TLS, right? Transport layer security. So again, this third option is basically not correct because IP does not have any security primitives at the network layer, right? But it has it at the higher layers. That's basically the answer to this. And D is one interest packet can fetch multiple data packets in NDN. So is this correct? So basically, if you the perspective you look at it is what matters here. So in NDN, so each interest packet, right? So it is meant to fetch a specific chunk of data only, right? So one interest does not automatically retrieve multiple data packets. So that's why D is wrong, right? Okay, let me just. Right. So that and the last option is the routing plane of IP is dumb, whereas the routing plane of NDN is smart. Okay, so this is also not correct. But why is this not correct? It's misleading. So why is it misleading? The term smart, because while Indian routers perform additional tasks. Characterizing the IP routing itself. Oversimplifies the design differences. Right? Which means you can't just like that call IP as dumb just because Indian performs some extra additional task during routing, right? So it's not exactly smart or dumb in this case, which is why the answers are as such. Right. So the next one is number 4. So which of the problems is slash are addressed by Indian name-based routing? Okay. Right. So the problems given here are address space exhaustion, NAT traversal, guarantee of no data loss, and address management. Okay. So address space. So let's look at what these problems are individually, and then let's look at what the answer to these questions are. Right now, if we look at address space exhaustion, so this is nothing but a consequence of IP addresses because IP addresses are either in IPv4, let's say, which is basically what we use, 2 to the power 32. So these are limited number of addresses. So there is a chance that the number of devices used in the world can go above and beyond this number, which they already have. So which is why they use IP multiplexing. But even then, you are left with very limited number of public IP addresses, right? So which will pretty much won't be enough. Which is why IPv6 came up. Right? So these are problems with traditional IP networks. Right? So this is address space exhaustion of address space. Right? NAT traversal. So NAT is network address translation. So this NAT is used precisely to counter the address space exhaustion. So it is basically a middle box which is sitting, and this is a public network, and this is a private network. So if you notice in all of your private networks, right, if you connect your phone or your computer to your router, if you type your IP address, if you type ipconfig or ifconfig on your command line, right, so you will get an address either starting from 192.168 blah 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 or 10.0 dot blah blah blah, or there's one more range. I kind of forgot the range. So these are all the private IP address ranges. So if you're connecting to a network in your home, you could have an address let's say 192.168.0.1, all right? And your friend connecting to his router at his home could also have the same IP address. So it's like this. Let's say this is you, your friend, right? Now, so of course, every device that's connected to the internet or to a router has an IP address. So you could have 192.168.0.1, and your friend could also have 192.168.0.1. So how does this work? You must have noticed this phenomenon, right? So how does this duplicity of IP addresses work? So it works because of something called NAT traversal. Because your organization or your network, right? So this is your home network, let's say. So this has an IP address, something called a public IP address. So every time a packet goes out of this network or comes into this network, if it goes out of this network, it will have the public IP address. If it comes into this network and comes over here, it will get translated into its private IP address. So these are all private IP addresses. Second, oh my god. Hmm. Okay. So these are private IP addresses. So IP addresses are reused, right? How? Using something called network address translation, which is basically network address translation. This is called NAT, network address translation. So this network address translation is happening because we don't have enough IP addresses. Okay. And the third one is guarantee of no data loss. Data loss could happen, right? So data loss happens. Why does data loss happen? It happens because of best effort. We just saw that above in a question. What is best effort, right? And address management. So address management is also something that is a bit of a problem now because you don't have enough addresses, and all the addresses are based on numbers and IP addresses. So in order to solve that, you have something called DNS, where you attach some words to these IP addresses and you translate that domain name or these words into, you know, IP addresses. And yeah, so this is pretty much what goes on, right, in this paradigm, in the current paradigm. Okay, so which of the following problems are addressed by NDN name-based routing? So, so one of the motivations. The actual answer starts from here. I was just explaining the context the uh, of the options, right? Indian is to alleviate challenges intrinsic to the IP address centric model. So how does that do it? NDN shifts the focus to naming content rather than specifying endpoints. So this one we know. This is basically what NDN is. Right. So now how does NDN address each of the above options? Let's just see that. So address space exhaustion, right? So with the move from location dependent addresses to content based naming, right? NDN circumvents the limitations posed by finite IP addresses. So A is something that is addressed. Well, let's look at B, NAT traversal. Because NDN communication is name based, right? Rather than address based, issues associated with network address translation, NAT, correct? Can be mitigated. So B is also an answer. And guarantee of no data loss is not an answer. Why? Because we just saw this in a previous question. both IP and NDN use best effort. So which means packet loss can still occur due to congestion or errors. Right. So basically congestion. So data loss is basically the way TCP works, right? So you kind of like overload the network in the beginning, and then you test the network, you push the network to the limits, and then you pull back, right? And then you slowly optimize the rate of data being sent. Again, this is when I'm talking about traditional IP networks. Indian pretty much does nothing more than that, right? It just changes the way in which content is addressed. Other than that, the transport mechanisms are all uh, not going to aid in guaranteed delivery. So which means C is not the case. And address management. So address management, um, it's pretty much obvious, right? So all of this A, B, and D, all of these talk about addresses. That's pretty much what NDN does. So managing names is more flexible than managing IP addresses. So this eases the complex address allocation. So which means the answer for this question is A, B, and D, right? So I think by this time, NDN should be pretty familiar. Now we can, I think, slightly increase the pace of our answering. Again, oh God. Some moment. Um, you just bear with me. I'm sorry about this. This is for the first set. 5, 6, 7, 8, 9, 10. Okay. Six, 7, eight. Okay. Okay. So which of the following is a key difference between CIS and PIT tables? Right. So what is this PIT? PIT is nothing but pending interest table. And CS is nothing but content store. Basically different names, that's all. Okay. So basically in NDN, we have content store. These are the three data structures. Facilitate packet processing. Right. Content store. CS. A cache that holds data packet. Okay. So basically what it does is it caches data packets that have already been retrieved so that future requests can be quickly satisfied. And this PIT So it is a table that keeps track of interests that have been forwarded but not yet satisfied. Okay. And the last thing is FIB, just forwarding information base. Right. So this is used for routing interests to the appropriate next hop. So these are the three things that the three data structures that I used. But now the question is, which of the following is a key difference between CS and PIT tables in Indian? Right? So A, the CS is used to forward interest to next hop, while the PIT is used to store data. No, we just saw, right? We just explained what CS is, PIT is. B, the CS is used to store the interest of the unresponsive data, while the PIT is used to store data. Again, the PIT is not used to store data, right? So that's what this is wrong. The CS is used to store data, while the PIT is used to store the interest of the unresponsive data. So CS is used to store data, and PIT is used to store the interest of the unresponsive data, which is pretty much correct as per our study so far below. The CS is used to store incoming interfaces, while PIT is used to forward interests to the next hop. No, I mean, I don't even know what interfaces mean. So it's pretty much. Right? So yeah, A, B, C, D. So the answer is C. Right. So 6. Which of the following is slash are the reasons why NDN may be more efficient than IP in terms of network resource usage? Okay. So what this question basically means is network resource usage. So this is a very broad term, but essentially what this means is if a network, so a network is like a road, right? It can have one lane of vehicles, it could have two lanes of vehicles, right? It could have two lanes, or it could be filled with vehicles. So the network resource is basically the width of the road and the length also, let's say, the width essentially. So if you only have one lane of vehicle in this, right? If there's only one lane of vehicle in this, that means your resource usage is 50% or less than 50%. But if you're able to use the whole width of the vehicle, then your resource is being used with the highest efficiency. So they're asking with the same analogy. So the width of the road is nothing but the bandwidth here. Right? The width of the road is nothing but bandwidth. They're asking which of the following are the reasons why NDN may be more efficient than IP in terms of network resource usage? Okay, now, why possibly could these reasons be? So, what NDN does is NDN's design is essentially it inherently is aimed at increased efficiency, right? But where do these efficiency improvements come from? So these efficiency improvements, they come from its caching and flexible forwarding strategies. So, okay. Caching and flexible forwarding. Right. So let's look at the options now. Data packet can be cached at intermediate nodes. Yes, true. This is a part of NDN. But why does it increase network resource usage? Because you free up more space for other packets to go. Essentially, instead of going all the way till the end, you get the particular data from an intermediate node. We were seeing this in the previous questions, right? So this is definitely something. So data packets can be cached at intermediate nodes, right? So this is correct. So interest slash data packets can be forwarded to multiple producers slash consumers. So so basically this is also correct because Indian's forwarding mechanism, so it allows interest and data packets to be distributed towards multiple potential sources or end users. So this is basically a multipath and a multicast friendly approach, and this can essentially optimize your network resource usage. Right? Okay, this is also correct. And C is interest packets are always routed towards the content producer via the shortest path. So although Indian uses the shortest path strategy, it is not always limited to this because routers may choose alternative paths based on resource availability and network conditions. So, therefore, this is a very broad statement which cannot be considered for this particular use case. So, C is not an answer. D. NDN networking paradigms do not pose data privacy or availability risks. Um, Again, NDN's architecture tends to introduce new challenges with respect to data privacy and availability. So, um, security measures should still be implemented, but it is not because it is not inherently free from such risks. So it gives rise to a new host of security issues, right? So this is also sorry wrong. So the answer is A and B. Okay? And now the seventh question is Which of the following statements is/are correct about naming in the Indian? Indian uses the hierarchical naming convention. So basically, if you look at Indian, names are fundamental components. They identify the content directly and are basically an integral part of the communication process. If you look at it as a whole, right? So, but which of these statements are correct about Indian? Indian uses hierarchical naming convention, right? So yes, it does use hierarchical naming. So it is very similar to URLs. So because of this, you can basically aggregate a particular resource under another set of resources, like server A slash movie one, server A slash movie two, something like that. So hierarchy. So this is basically if you can hierarchify the naming convention, then you can basically it can kind of gives you the metadata regarding the data itself. The name itself gives you the metadata. Okay. Names are generated by application. Right? So applications basically, yeah, is also true in Indian. Applications generally have the flexibility to generate names which are based on either their own requirements um, and the data structures that is supported by the application. So A and B both are correct. Now C says that users slash application developers do not have the ability to define their own naming convention. So it is not the case. You can have your own naming convention, right? As long as it follows certain rules dictated by the Indian. So and then D, although Indian primarily uses hierarchical naming, it does not explicitly uh, exclude schemes for a specific application. So even though hierarchical model is what is used, um, it can still use flat naming. It can still use flat naming. There is no problem here. So flat naming can still be used. All right. So so the statement is wrong. So which are the correct statements? The answers are A and B. Eighth one. In a standard Indian architecture, how many data structures does each router typically maintain in order to process Indian packets? Um, so this is they're asking in a standard Indian architecture. Um, so we just saw this before. So what is the answer? The answer is the three. Why? What are the three? So the three data structures are content store, next is pending interest table, and forwarding information base. So this is pretty straightforward. Now at number 9, so which of the following statements is/are incorrect about security in Indian? Security in Indian. Let's just go through the statements and then let's see which of them are correct or incorrect. Let's see. So the content producer will cryptographically sign the data packet. Yes, this is true. And why is this done? So this is done because you want to verify who generated that particular piece of data. You want to make sure that it's coming from the right person. So if we say that, let's say an organization like, mm, let's say if Microsoft produces a piece of data, then we need to be sure that it's coming from Microsoft. Someone from outside should not come and tell us that, I Microsoft produces data, here, take it. You need to be able to verify this, right, in an objective way. So how can you do that? You can do that by looking at the fact that the data that is being given to you is cryptographically signed, right? So this is true. System cannot be attacked using information obtained from the identifier. So it actually can be attacked, right? Um, Even though the design minimizes risks linked with identifier based attacks, but no particular system is completely immune to all forms of attack. You definitely will come up with folks trying to social engineer, I mean, basically trying to engineer their way inside these um, new systems, right? So this is also true. So NDN uses end-to-end encryption to protect content in transit. Yes. Sorry, it does not. It does not essentially, mandate. Although NDN encryption can be used, NDN does not completely depend on end-to-end encryption. So to secure its channel, right? So it uses only signature-based verification, which was basically the first option. So this is not true. So encryption is mandatory for the data packets transmitted over the network. Again, no, it is optional. It is not mandatory. Okay. So this is false. So the answers are C and D. What is the role of the NDN trust model? Um, Let me just write this one down. The trust model in NDN is designed to secure the network by establishing mechanisms for verifying data, right? And so basically, what this does is instead of solely relying on securing channel, solely relying on secure channels, Indian embeds security into the data itself. Okay, so what is the role of the trust model? So it basically focuses on authenticity. Basically, this basically confirms that the content comes from the stated producer, and integrity ensures that the data has not been tampered in transit. On its way, that is. So basically, if you look at the options now, if we kind of like look at it, we can see that the role of Indian's trust model is to ensure data availability. No, not really. Is it to ensure that packets are successfully delivered to the requester? No, not this also, because that's like it's only best effort, right? It's not, there's nothing to do with guaranteeing delivery. Ensure that data authenticity and integrity. So to ensure data authenticity and integrity, yes, this is what we just saw. To manage network resources, no. I mean, it doesn't make sense, right? So the answer to this is C. Right. So I think we can. So we have another set of 10 questions. So what we'll do is we can, since we have an extra class on Tuesday, we look at the next set of questions on Tuesday. And if we have time, we can take a look at P4 as well, just briefly, just to give you a short flavor of what you've studied here in a practical, through a practical lens, right? So yeah, we can, I think, conclude the session if you don't have any questions, and you're free to leave, right? And I'll put up the recording on YouTube very soon. All right. Okay. Thank you, guys. I'll be here for another 5-10 minutes. Or you can leave if you don't have any further questions. You can leave.